طيب يعطيكم العافية. خلينا اليوم نكمل الجزء الثاني من الانتي كانسر ايجنتس. بلشنا بالجزء الأول وحكينا شوي عن الالكيليتنج ايجنتس. ذكرنا مثال عليهم اللي هم النيتروجين ماسترز أو الفيرست جروب اوف ذيس alkylating ايجنتس اللي هم النيتروجين ماسترز. اليوم راح نكمل بالالكيليتنج ايجنتس وراح نكمل بالنيتروجين ماسترز. حكينا عن 3 نيتروجين ماسترز سابقا، حكينا عن البنداميوستين وحكينا عن اللي هو ميكلوثامين. اليوم راح نحكي عن السايكلوفوسفامايد. And the cyclophosphamide is another example on a nitrogen master. There are specific type of nitrogen master, there are special type of nitrogen master. لأنه فيهم different characteristics than the previous one. Specifically, cyclophosphamide itself has the cyclophosphamide itself is a chiral prodrug. It's a chiral prodrug, which means it's a prodrug needs to be activated to become the active form, or to get to its active form. And then it's chiral as well, because the reason why it's chiral, as you can see in the structure, here's the structure of cyclophosphamide. In the structure there is a chiral center, and that's why it's a chiral prodrug. The chiral center, in fact, it's the phosphate. The phosphate is chiral because there is 4 different groups attached to it: the oxygen, the nitrogen, this oxygen with the alkyl group, and the nitrogen here with the alkyl group. So the cyclophosphamide is prodrug because of the presence of the phosphate moiety. Now, cyclophosphamide itself is not active. It needs to be activated by specifically cytochrome B enzymes that exist in the liver. And this cytochrome B, what it does a regioselective hydroxylation at carbon number 4. And if you know which carbon number 4 is this one, this specific carbon over here is carbon number 4 that's next to the amine, because oxygen is number 1, 2, 3, and 4. So the cytochrome B oxidize this carbon to generate an intermediate that we call carbinolamine. Carbinolamine degrades further on its own spontaneously to generate the active form in 2 degradation steps. خلينا نشوف the pathway, how this happens specifically, the activation of cyclophosphamide to its active form. هلا السؤال المهم اللي لازم نحكيه إنه النيتروجين هون, this nitrogen when it's part of phosphamide, يعني attached to the phosphate here, is not active enough to generate the aziridine ring or the aziridinium ring. The reason why? Because this nitrogen participate or donate its lone pair of electrons to the phosphate. زي النيتروجين لما تكون جزء من carbonyl moiety. لما تكون جزء من carbonyl moiety, nitrogen, basically this nitrogen lone pair are not available, they're not nucleophilic because they contribute to the resonance of that carbonyl. نفس الشيء الphosphate. So the nitrogen here, although this structure has the ethyl chlorine moiety or the chloroethyl moiety اللي حكينا عنهم اللي موجودين كل النيتروجين ماسترز that generate the active aziridinium ring اللي حكينا عنها بالمحاضرة السابقة. This nitrogen is not nucleophilic enough to do the nucleophilic attack and generate the aziridinium ring because it's next to this phosphate. So this drug needs to be activated. This nitrogen needs to be made more nucleophilic in order to be able to generate the aziridinium ring formation. And so this is how this activation step happens. You have the cytochrome B enzyme in the liver. Once this drug cyclophosphamide administered into the patients, the liver's cytochrome B's oxidized carbon number 1 اللي حكينا عنها سابقا, which exists on this position, the carbon next to the amine, this carbon specifically, okay? And so you can see that this, after cytochrome B oxidation, this carbon gets a hydroxy on it, on the position of that carbon. So it's an oxidation where we transfer the hydrogen to hydroxyl group. Now this carbon number 4, has 2 functional groups, has an amine and has a hydroxy. When a carbon has an amine and hydroxy, so the same carbon has nitrogen and hydroxyl group or oxygen, we call this carbon as carbinolamine. So this intermediate is called as carbinolamine moiety. Okay, if you want me, I can draw this as well to just make sure everyone knows that specifically what carbinolamine is like. And this is the carbinolamine. It's a carbon. You have oxygen and then nitrogen. Okay, so there is an oxygen, nitrogen. This moiety is called as carbinolamine, as you can see, and this is your carbinolamine moiety at carbon number 4. Carbinolamine moiety is not stable. similar to hemiacetal or hemiketal. ولو سمحتوا دوروا شو على الهemiacetal وhemiketal. Hemiacetal and hemiketal, they're not very stable structures. They degrade spontaneously on their own. They degrade without any need of enzymatic action. They degrade to hemiacetal degrades to aldehyde and alcohol. الهemiketal degrades to ketone and alcohol. الكربينولامين هون اللي هاي البوزيشن basically can degrade to carbinolamine, which means can degrade to aldehyde and amine. راح تتحطم to aldehyde and amine. راح تنكسر هاي الرابطة between carbon and nitrogen. You will generate this aldehyde moiety over here, and then you leave behind the amine, the free amine. So this compound is called aldephosphomide. Why it's aldephosphomide? Because we have an aldehyde and we have a phosphamide moiety, high phosphomide moiety, as you can see over here. And so what happened here is a ring opening, spontaneous degradation of carbinolamine. هاي ring فتحت تركت وراها aldehyde and amine. We call this as aldephosphomide. Okay. طيب هلا الالدوفوسفاميد, this is the first degradation or hydrolysis step. Hydrolysis هي basically the degradation step that happens. الالدوفوسفاميد, وخليني امسح هذا الجزء اللي رسمته عشان نرجع نشوف الستركشر, clean structure again. Okay, so the aldephosphomide also go through a second degradation step where your aldehyde leaves with its 2 carbon next to it. So this is the moiety that leaves. It leaves as specifically acrolein, as you can see. And acrolein, as we will see later, is a toxic byproduct from this reaction. So that aldehyde moiety leaves as acrolein. Okay, and the way this happens, basically through what we call a beta elimination. Why it's beta elimination? Because we have an alpha carbon, beta carbon. The bond between beta and the oxygen breaks here to eliminate this acrolein moiety, and that leaves behind this oxygen in the structure. This is very important for the next step. So the oxygen stays here with the phosphate. Here is the oxygen that stays over here, as you can see, and it's negatively charged. This is at physiological pH. This phosphate will be negatively charged. The reason why it's negatively charged, because the pKa of that oxygen, if it's hydroxy, is 4.75. which means it's an acidic pKa. It's acidic compound at physiological pH. So it will be negatively charged, this oxygen. هاي الأكسجين من وين إجت؟ left behind after this acrolein moiety اللي طلعت, اللي عندنا هذا الجزء تبع الأكرولين moiety اللي طلع ترك وراه الأكسجين. الأكسجين جزء فعليا من phosphoramide. So that structure is called phosphoramide mustard. Why it's phosphoramide mustard? Because this is your phosphoramide. Okay. And this is your mustard moiety. Alright? And so in the phosphoramide, راح امسح هذا اللي كتبته عشان يكون easier to see. In the phosphoramide, we have this oxygen that's part of the phosphoramide. Think of it as phosphoric acid. So this oxygen is acidic, similar to what we have oxygen in phosphoric acid. Phosphoric acid is an acidic compound. الأكسجين اللي موجودين فيهم نفس الشيء الأكسجين الموجود في phosphoramide is acidic. So if it's acidic, at physiological pH will be ionized and negatively charged. This negative charge فعليا هو electron density, high electron density. It will donate electron to phosphate. It will donate electron to nitrogens. So if the nitrogen has more electrons, now the lone pair of electrons on the nitrogen can be nucleophilic enough to do the aziridinium ring formation اللي شفناها بالمحاضرة السابقة, where you have an attack on this beta carbon and the chlorine leaves as a good leaving group. So only after you see this oxygen negatively charged at physiological pH, يعني after the leaving of the acrolein, when you expose the oxygen, now the oxygen is negatively charged, it increases the density of the phosphate and it increases the density of electrons على nitrogen as well. So the nitrogen become more nucleophilic. It can attack the beta carbon to generate the aziridinium ring that you can see over here. And so this only happens after the degradation or the elimination of that acrolein moiety. You have negative charge on oxygen, nitrogen lone pair is nucleophilic enough now to generate the aziridinium ring. Now the aziridinium, as we have seen in المحاضرة السابقة, is the reactive form of your nitrogen mustards. It alkylates the DNA bases, binds to it, and destroys the DNA and kills the cancer cell. This is the main route. There is a second route, less important, where this phosphoramide moiety degrades further. راح تطلع as phosphate and amine as well. هذول التو moieties راح يطلعوا، راح يتركوا وراهم just the mustard part اللي هو basically the very basic mustard, the most basic structure of mustard, the bis beta chloroethylamine. وهذا structure itself can also make the aziridine, because the nitrogen here is nucleophilic enough. It will make the aziridine ring. It will be positively charged at physiological pH because the amine are basic. So you have the aziridinium ring here, and aziridinium is very reactive, as we said earlier بالمحاضرات السابقة لسببين. The highly strained ring and the positively charged nitrogen in the aziridine makes those carbon highly electrophilic carbons can be easily attacked by nucleophiles from the DNA. واضح؟ فعندنا two main pathways. المين pathway اللي هو أهم واحد after the phosphoramide mustards بصير عندنا formation of aziridinium ring. Second pathway you could see a further degradation step where you leave where the phosphoric acid leaves and ammonia. يعني الفوسفوراميد moiety بتتحطم لphosphoric acid وammonia as we can see here, and then you leave the mustard part that make the aziridine ring which is reactive form that do the DNA alkylation. واضحة؟ Alright, so هلا خلينا إذا نلخص اللي شفناه هون. Oxidation of cyclophosphomides, further degradation generate phosphoramide mustards. This phosphoramide mustards give you the aziridinium ring. طيب هلا حكينا عن الأكرولين. رح أرجع لنقطة الأكرولين اللي طلعت. الأكرولين is pretty toxic compound. It's an electrophilic moiety. زي الأزيريدينيوم. Less reactive but electrophilic moiety and can cause toxicity for the cells. So as we said بالسلايد السابقة, الأكرولين generated by the degradation of our previous compound اللي هو to generate the phosphoramide. هو بيطلع من تحطه بالألدوفوسفاميد to phosphoramide. And as I said, acrolein is an electrophilic moiety, strongly electrophilic moiety. Not as strong as aziridinium, but still electrophilic enough. Usually this oxidation step اللي حكينا عنها سابقا by liver activation of cyclophosphamide happened by the cytochrome B in the liver. So acrolein mostly generated in the liver. And now in the liver we have a protection mechanism to prevent any toxicity from this acrolein. And that protection mechanism بالliver or other parts of the body or other cells of the body is the glutathione. Glutathione is basically a compound that has a free thiol, and that free thiol is nucleophilic, that has two lone pair of electrons. راح يعمل attack على electrophilic moiety of acrolein to generate this adduct. This adduct is safe and can be eliminated by the kidney. المشكلة إنه الكدني والبلادر, kidney and bladder try to recycle glutathione. So what they do if they see glutathione, there are enzymes that regenerate glutathione in the kidney and bladder. And when you regenerate glutathione, راح تطلع acrolein again inside the kidney and the bladder. And so that if the acrolein present in the kidney and the bladder, they will cause severe toxicity for the kidney and bladder. So there is ways to prevent or reduce this type of toxicity from cyclophosphamide. The main way is that you give the patient a drug that's called MISNA. This is the MISNA structure, as you can see. With MISNA, you can either give it to patient orally or you can do a bladder irrigation with this MISNA to reduce cyclophosphamide toxicity, to reduce the toxicity اللي جاية من الacrolein after activation of cyclophosphamide. المسنا as you can see has a thiol زي glutathione فعليا, فهو عبارة عن يعني compound with a free thiol similar to glutathione, smaller structure, and that thiol will react with this beta carbon of the acrolein راح يعمل عليها nucleophilic addition to generate a MISNA adduct between the MISNA and the acrolein, which is a water-soluble compound that can be easily excreted from the kidney. So the main way, if you want to give to reduce toxicity of cyclophosphamide, usually you do a bladder irrigation with MISNA to prevent the acrolein toxicity generated from activation of cyclophosphamide. Okay, That should be clear. إذا مسنا أهميته نعمل في bladder irrigation to reduce الأكرولين toxicity اللي جاية من activation of cyclophosphamide. طيب خلينا نشوف another example. إذا حكينا عن cyclophosphamide, chiral product needs activation by liver enzymes, and this generates acrolein that's toxic, but also generates activated form اللي هو phosphoramide mustard that generate the azidinium ring that does the DNA toxicity and kills the cancer cells. Another example عندنا اللي هو ifosfamide. It's very similar structure between cyclophosphamide and ifosfamide. You can see ifosfamide, except the main difference between cyclophosphamide and ifosfamide, two chloroethyl moieties. They're not both of the same nitrogen. كل واحدة فيهم على nitrogen مختلف. You can think of them as the two arms of the mustard are in two different nitrogen. So they're very similar in everything, ifosfamide, except has a little bit lower toxicity in other places, but higher bladder toxicity. So it's more specific to cancer cells, was found to be more specific to cancer cells, but unfortunately produces higher bladder toxicity. It also requires metabolic activation by cytochrome B enzyme, cyclophosphamide, as we have seen earlier. Okay, هلا بدنا نحكي عن another example of alkylating agent. مش nitrogen mustards, هم a newer class more than the nitrogen mustards that we call them as nitrosourea. So nitrosourea are another example of alkylating agents. هيك بنكون خلصنا nitrogen mustard سابقا. حكينا عن examples of nitrogen mustards. آخر two examples حكينا عن cyclophosphamide و ifosfamide. هلا راح نحكي عن nitrosourea. This is another example على alkylating agent. These are unstable structures that decompose readily in aqueous environment. أهم شيء بدي إياك تعرفوا عنهم of those compounds اللي هم nitrosourea, that these compounds are stable in pH around 4.5. Anything lower than that or higher than that, they degrade spontaneously بصير فيهم decomposition. They generate reactive byproducts that cause toxicity for the cell or they kill the cell. So what that means that in physiological pH, if you administer them to patient nitrosourea or to specific subject or person or human, the physiological pH is 7.5. حكينا هم stable only at pH 4.5. So at 7.5, these compounds will degrade spontaneously. ما بيحتاجوا لأي enzymatic fragmentation or activation. What they need just some higher pH or lower pH than 4.5. We'll just say 7.5. فلما نحطهم بال 7.5, basically they degrade spontaneously, generate an active form of their structure or active byproducts that attack the DNA and kill the cancer cell. خلينا نطلع على structure of nitrosourea. Here's the structure of nitrosourea compound, one of the examples or the main structure or formula for those nitrosourea. You can see this is a urea moiety. شو اليوريا moiety؟ هون راح ارسم اليوريا moiety فوق. كل المفروض يعرف شو اليوريا moiety. This is a urea carbonyl وعليها 2 nitrogens. Okay, there's 2 nitrogens على هاي carbon. So you can see this is the urea moiety in the structure here. This is your urea over here, and this is your nitrose اللي هي N double bond O. So that's why we call it nitrosourea. We're in a nitrose moiety over here, and then we have a urea moiety over here. So the nitrosourea at pH 7.5 is not stable as we said. What happens and the nitrogen horn over here, خليني امسح اللي رسمته عشان اوضح الصورة افضل. So the nitrosourea at physiological pH, basically it's considered a basic pH for nitrosourea because this amine proton is acidic at physiological pH. So physiological pH 7.5, the pK of that amine is about 4.5 to 5, which is why it's acidic because it's part of an amide. So at the physiological pH, this amine will lose the proton, generating this negatively charged nitrogen, which will collapse down. This nitrosourea species will collapse down to release two compounds, the diazo hydroxide and the isocyanate. The diazo hydroxide is basically diazo group, which is N double bond N is called diazo, and then we have the hydroxy group attached to it. That's why we call it diazo hydroxide. And then we have the isocyanate, cyanate, which is basically a carbonyl and amine attached to it. Now, so this is the spontaneous decomposition of nitrosourea at physiological pH. We said nitrosourea at pH around 4.5 or 5 is stable. Above or below that is not stable. So in physiological pH, this proton gets abstracted from the amide, decomposes spontaneously once you have this negatively charged species to release two compounds, diazo hydroxide and then the isocyanate. Okay, so the important one that we're going to talk about is the diazo hydroxide. Diazo hydroxide further decomposes to lose a water molecule, and for this to happen, this double bond, not double bond, lone pair on the nitrogen, on the second nitrogen, will push its electrons to make a triple bond with the next nitrogen, and in exchange of that, this OH will leave, take its electrons in the bond and leave. This will generate this compound that we call as diazonium or diazo. Nitrogen and then triple bond nitrogen is called as diazo. Okay, they're called as diazo, and because they have a positive charge, sometimes they're called as diazonium. Now, diazo or diazonium is very unstable. It also spontaneously decomposes to release nitrogen gas and leave behind the carbocation. So the bond here, electrons goes back to the nitrogen, as you can see. So the arrow should be pointing toward the nitrogen that's positively charged. And then when that happens, you break this bond over here, leaving the nitrogen gas and leaving also behind this carbocation species. That carbocation species is a very reactive species. How the species is very reactive? It's an electrophilic moiety. طبعا لأنه عليه positive charge, with DNA is a nucleophilic because of the nitrogen, تبعون guanine specifically. They can do a nucleophilic attack and make a covalent bond with that carbocation species. Now we have chlorine, also a good leaving group. So a second guanine from the other DNA strand will come and attack on this carbon over here to release this chlorine moiety, generating the alkylated, the two DNA strands alkylated together in one species. As you can see, this is one DNA strand, second DNA strand, both are alkylated together, and you can see this is going to cause damage for the DNA and eventually killing the cancer cell. So the important thing I want you to know that your nitrosourea compound decomposes at physiological pH to give two compounds, diazo hydroxide, isocyanate. The one that's important to do with diazo hydroxide, it decomposes further spontaneously to lose water molecule, leaving behind diazo or diazonium species that has a positive charge. With diazo راح يصير كمان a second decomposition. It's again spontaneous decomposition. Colloidal process spontaneous, ما في any enzymatic reaction to release nitrogen gas as well as the carbocation, which is the reactive species. زي ما كنا نحكي قبل اللي هو الازيريدينيوم ring is the reactive species. هنا carbocation ring, carbocation عفوا is the species that's reactive, reacts with the DNA and do DNA alkylation and damage the DNA. Alright, so these are the nitrosourea compounds, and this is the general molecular formula, general mechanism on how they work. And so the two examples that we have on nitrosourea is carmustine and lomustine. The carmustine is an older one, the lomustine is a newer one. Look at the two structures of carmustine and lomustine. They are both nitrosourea. We have this nitrosourea moiety here, and we have this nitroso as well in the lomustine. And both of them, as you can see, are highly lipophilic structures. So these compounds can cross blood-brain barrier, and in consequence to that, you can use them for treatment of brain tumors and Hodgkin disease, because you need compounds to be lipophilic to cross blood-brain barrier, and those do, so they can be used for treatment of brain tumors. And so both are nitrosoureas. They're just different in the side chain here. This side chain is one of them has a chloroethyl, the other one has a cyclohexyl moiety. And both of them react in the same way or kill the cancer cell through damaging the DNA by alkylating DNA. نفس الميكانيزم اللي حكينا عنه سابقا بالنيتروسيوريا. طيب هلا حكينا هذول الكومباوندز. They're highly lipophilic compounds. So if you want to administer to the patient, the only way to do this is by IV administration. And by IV administration, water is not going to dissolve it. Only water is not going to dissolve it. So you need to use a co-solvent. And typically the co-solvent is used is 10% ethanol. So you have a vial of the powder and the second vial of the solvent in the same box. And then you take that liquid in the second vial, you add it to your powder and you dissolve it. That liquid is 10% ethanol in water. And ethanol is lipophilic, works as a co-solvent to dissolve your lipophilic compound. So this compound is given to patients to treat brain tumors, but either the carmustine or lomustine, both of them, they can be given, one of them or both of them can be given for treatment of brain tumors. As we said earlier, most of those compounds alkylating agents are non-selective, non-specific, so they could cause secondary cancers, as we have seen earlier, and the most common one is really leukemia that's caused by those compounds. So the next two compounds I'm going to talk about are procarbazine and dacarbazine. Those two compounds are miscellaneous alkylating agents, and the first one is procarbazine. Is an originally developed compound as monoamine oxidase inhibitor, which are antidepressants. So these compounds initially developed as monoamine oxidase inhibitors. Later on, they were screened by a national institute in the United States called National Cancer Institute, and they were found to kill cancer cells. And so they stopped using it for antidepressant activity, and they started exploring it for its anti-cancer activity. They found it to be a very potent anti-cancer compound, and it's a compound that needs a metabolic activation by Cytochrome B enzyme to do the DNA alkylation. And the DNA alkylation happens here through a free radical mechanism. It's different than what we have seen earlier in nitrosourea. nitrosourea بيشتغلوا شو المين reactive species with nitrosourea اللي هم الكربوكاتايونز that are the ones that do the alkylation. طيب نفس السؤال لو سألناه بحالة الكومباوندز اللي درسناهم قبل اللي هم النيتروجين ماسترز. شو reactive intermediate? Reactive intermediate in that case was the azilidinium ring that really alkylate the DNA. هنا the procarbazine, the reactive intermediate is a free radical. Okay? And that compound needs a metabolic activation by cytochrome B to do its activity. Alright, so let's look at this. Procarbazine compound has this nitrogen functional moiety. And this nitrogen functional moiety is called as methyl hydrazine, or sorry, these are hydrazines. Okay, and so the procarbazine is a compound that has hydrazine functional group, as I mentioned. The hydrazine is nitrogen, single point nitrogen. This functional group is called hydrazine. Okay, so procarbazine needs to be activated by cytochrome B first to do its activity. And the way it's activated, this hydrazine gets oxidized by cytochrome B to N double bond N, and that functional group, as we said earlier, is called diazo. And so this procarbazine is converted to azoprocarbazine because it has an azo functional group or diazo functional group. And that azoprocarbazine degrades further by the reaction with the cytochrome B again. So this is a second cytochrome B oxidation. The first one happened to convert procarbazine to azocarbazine. Now azocarbazine is further oxidized by cytochrome B to release two compounds. One of them is the benzaldehyde compound, لأنه في aldehyde بنسميها benzaldehyde, and the other one اللي هو الميثيل diazine. Okay. طيب هلا كيف صار هاي specifically هاي الستيب؟ أنا بدي أطلب منك إنك تعرفها وراح أسألك عنها بالامتحان، فأنت رجاء تطلعها وتعرف كيف هاي الميكانيزم happen. How does the azoprocarbazine through the cytochrome B oxidation. Where exactly the cytochrome B oxidation happen? To generate the benzaldehyde and the methyl diazine. Okay, so you need to know where this cytochrome B worked on azoprocarbazine to generate those two compounds, اللي هو benzaldehyde and methyl diazine. The methyl diazine, as you can see, is a compound that can easily degrade to its radical byproducts, and these are the radical byproducts produced: methyl radical, a proton radical, and nitrogen. And if you want me to draw the mechanism, I can do. You could ask or drop that question for me on Facebook or somewhere else, and I can draw the mechanism. So the most important thing that you should know that there's a methyl radical being generated from methyl diazine, because methyl diazine spontaneously decomposes to nitrogen gas and then the methyl radical. That methyl radical is very reactive, can easily react with an electron-rich atoms like the one in nitrogen in nucleic bases, and specifically the guanine أكثر واحد that's exposed to those radicals. So the methyl radical will react with the guanine and do a guanine methylation. And once this happens, the guanine methylation, you're basically causing mutation for DNA and causing death for that cancer cell. Okay? All right, so the last one that I'll be talking about is the dicarbazine. And the dicarbazine is a compound that kills cancer cells through a reactive intermediate. Reactive intermediate on a carbocation. The carbocation you'll see, it's a the reactive intermediate that reacts with the DNA and alkylates the DNA. Similar to what, as we have seen earlier, similar to nitrosourea. كمان nitrosourea حكينا reactive intermediate or reactive species that reacts with DNA is also carbocation. So the dicarbazine, as you can see here, has this moiety or this. So the dicarbazine, as you can see, has this moiety or this part where we have the 3 nitrogen attached to each other. These are called triazo. So the triazo group has 2 terminal methyls attached to it in the dicarbazine. Now this compound again requires enzymatic activation. It's a prodrug similar to procarbazine. So you need an enzymatic activation. Different than nitrosourea ما بيحتاج enzymatic activation. At just physiological pH, they decompose quickly, generate their carbocation. Here you need enzymatic activation. With the assistance of liver enzyme, cytochrome B450, one of those 2 methyls will be oxidized to generate this intermediate. هلا بدي تلاحظ بهذا الانترميديت اللي بدي احط عليه الدائرة هون، لازم انت تعرف شو اسم الفانكشنال جروب. هاي اللي هون حكينا عنها قبل شو او ببداية المحاضرة. السايكلوفوسفاميد، كربون عليها اكسجين عليها نيتروجين، نفس الكربون عليها اكسجين and nitrogen. This carbon is called carbinolamine and it's unstable. It likes to degrade to go to its 2 components that it was generated eventually from, اللي هم الكربينولامين حكينا degrades to aldehyde and amine. الالديهايد اللي راح يطلع بهاي الحالة اللي هو formaldehyde. As you can see, this is the byproduct that leaves formaldehyde, leaving behind just the amine. And that amine has an extra one additional methyl. ما بيهمنا، بس بيهمني تعرف إذا الميتابوليك activation هنا by liver enzyme just removed 1 methyl through oxidation of that methyl. طبعا هاي البروسيس اللي أخذوا medicinal 1 المفروض إنهم يتذكروا. It's basically a dealkylation through cytochrome B oxidation. Cytochrome B oxidation or metabolism, or phase 1 metabolism, one of the main ways it metabolites those small molecules or drugs. الميتابوليزم step اللي بتصير عليها اللي هي dealkylation. One of the main يعني pathways for metabolism for those drugs. And this is an example of the same process اللي dealkylation، لأنه شلنا methyl by oxidizing it first and it will leave as formaldehyde. So هنا شلنا مثل واحدة من ال 2 methyls اللي على النيتروجين. Once this happens, now you have this species which can decompose spontaneously to generate the methyl diazonium. الميثيل diazonium اللي هو عندنا methyl attached عليها النيتروجين triple bond nitrogen. حكينا الديازونيوم هنا او الديازونيوم ديازو او الديازونيوم حكينا عنها سابقا بحالة النيتروزيوريا. نفس الشيء عندنا methyl diazonium هون. Methyl diazonium degrades further to kick out nitrogen gas and leaves a methyl carbocation or methyl carbonium ion that we call. Okay, so that methyl carbonium ion is a methyl that's highly electrophilic لأنه عليها positive charge. يصير في عليها nucleophilic attack from the guanine oxygen, and that guanine oxygen or nitrogen, doesn't matter which one, will be methylated or alkylated to generate the methyl guanine, which is the methylated DNA, and this is a mutation for the DNA. It will cause the cancer cell to die. Okay, so the main thing that I want you to know from this scheme is they have dicarbazine by metabolic activation. You lose one of the two terminal methyls على triazo group that we have seen, and then it leaves behind this intermediate. ما بيهمني كثير تعرف هذا الانترميديت، بيهمني تعرف اللي بنتج منه اللي هو مثل diazonium. مثل diazonium is the reactive intermediate. Diazonium بتطلع ال N triple bond N as it leaves, it takes الالكترونات اللي موجودين بالرابطة هون, and it leaves basically as nitrogen gas, leaving behind the methyl cation that we call it methyl carbonium ion, and that methyl carbonium ion reacts with the DNA guanine to methylate it or alkylate it, generate the all-methyl guanine. That's basically mutated DNA. صار عليها modification, it kills the cancer cell. Okay, so those are two miscellaneous compounds, procarbazine dicarbazine. Procarbazine بيشتغل عن طريق generation of free radicals, and free radicals will kill cancer cells, and they could kill normal cells and cause toxicity as well. The same thing here dicarbazine. Dicarbazine بيشتغل بطريقة مختلفة. الانترميديت اللي هو الكربوكاتاين مش free radical. This compound is used for treatment of malignant melanoma and in combination with other agents in treatment of metastatic melanoma as well. So it's mostly used for treatment of melanoma. Okay. Next group of alkylating agents اللي بنحكي عنهم اللي هو organoplatinum complexes. Organoplatinum complexes are antineoplastic agents that contain or they have an electron deficient metal atom. This electron deficient metal atom act as a way to or represent. So this electron deficient metal atom acts as an electrophile moiety, and that electrophile moiety will be attacked by the electron-rich DNA nucleophiles. Like similar to nitrogen mustard, as we have seen earlier, aziridinium ring is basically a high electrophilic ring, will be attacked by the nucleophilic DNA or the nucleophilic basis of the DNA, specifically from the nitrogen. If we want to look at those compounds in the cisplatin, carboplatine, oxaplatine, columpium platine, and this platinum is basically your electrophilic center. It has two chlorines in the cisplatin and two amines. راح نحكي عنهم in details المحاضرة القادمة, بس أنا حبيت أشرح small introduction on organoplatinum complexes to be aware that we're going to start with organoplatinum complexes في المحاضرة القادمة.